Okay, good morning. Last week we started to discuss different distribution, especially last week we focused on the exponential distribution, and then the main characteristic for exponential distributions in the end that the failure rate will be equal to the constant. So that's why this is a reason that the exponential distribution is always to be considered in the first sense because of the constant failure rate is the easiest one to deal with. But for sure that the exponential distribution is not enough to describe all the failure distributions in all of the case. So therefore, we still have to introduce some additional distribution, and then one that we will start to talk about today is the first one, the log-normal distributions. So the shortcomings in the exponential function have proven that we have to use the alternative distribution function to model the reliability data. And one of the most popular of these distribution is the one we call as a log-normal distribution. Functions. So as shown in this equation, this is a PDF for the log-normal distribution function. And as you can see, this is a function where that is not easily for the hand calculating, but it's very often used. And based on the logic what we have been lectured last week, that we first will talk about the PDF, and later we will start to talk about the CDF. So that's a PDF function for the log-normal and CDF function for the log-normal. And in the end, we will talk about the failure rate function, which is also called as a Hazard function, which is shown in here. And because of the calculation for this equation is not easily can be done by the hand calculating, so we will only show the result here, but the most important is to understand the implication coming from this distribution. So here is a slide we will talk more about the important implication that why we were particularly interested in the log-normal distribution function. And the log-normal distribution function can be shown from this equation, and there are several key parameters we have to pay attention. The first one is this one, the mu. So the first is mu, which has a physical significance of representing the median time. Or we call this as a time which 50% of the distribution will fail. So which is equal to mu is equal to natural log T50. So that's the meaning of this mu. That's the median time, which is also equal to the total 50% of the distribution that reach the time that the 50% of the distribution will reach to fail. That's we call as a T50 here. And second, there's a shape parameter that we call as a sigma here, which is strongly here, which strongly influence the shape of the small ft and also the capital Ft here. So as the logic we have been shown, the first one we will draw the PDF, which is this one. So this is our PDF function. And then because of the shape factor of the sigma will highly influence of our TDF. So we can see with a small sigma, we have this PDF function. But as long as we increase the sigma, then we will become the curve like this one. So that's why the shape parameter will highly influence the shape of the PDF and also the CDF. So therefore we can also see with the small shape factors reach to the larger shape factors here, so that can have the different shape for the CDF and PDF and CDF. And the larger value of sigma, usually when sigma is larger than 2, reflects the initial high value rate of the decrease with the time. So we can see that with a larger sigma here, this is a larger sigma here. Based on the PDF and CDF, in the end we can also calculate this Hazard function, and then with the Hazard function we can see with the shape factor increase, this is shape factor of 1, but if we have the shape factor of the 2, then we will have the curve like in this way. So this is a sigma larger than 2. So this suggests that initially we have very higher value rate, right? Because of this is with respect to time, and this is time 0. So at the time 0 we have a larger value rate, but with the time increase, then we start to gradually decrease here. And then we have to explain more about the importance of this value function, this Hazard function, because as you probably still remember that when we talk about the lifetime for the one product, we always use the concept of this best tube curve. And then with the best tube curve, we can have the 3 different regions, which in the beginning we have this this is a best tube curve. And then we can divide this best tube curve with the 3 regions. The first one is what we call the infant mortality. And then second one is what we call the steady. And then the last one is what we call the wear out. So that's the lifetime for the one product from the beginning phase in the end to the complete fail out, that we always experience all these 3 phases. And the powerful to use the log normal distribution is we are able to model these 3 different phases by consider the different sigma, which is a different shape parameter. So if you try to look at the region here, so if we try to tune the shape factor with a larger sigma, actually we can have the characteristic very similar to the case of the infant mortality, right? Because of now you can see this kind of the characteristic which is exactly equal to this part, right? So then we can leverage the different shape parameter in order to model the different phase of the lifetime. So that's the case with a larger sigma. But now if we try to slowly decrease the sigma, we are able also use one distribution function like here with the steady, which will be able to model the phase in the second one, which is steady. And also, if we decrease the sigma as a smaller, then we are able to model the wear out case, which is the third phase. So therefore, powerful by using this log-normal distribution, we can only use one function, but consider the different shape parameter, and therefore we are able to model the first phase, which is the infant mortality, the second phase, which is steady, and also the third phase, which is wear out. So that's why for the value reliability modeling, the log-normal distribution is considered as one of the popular use, because of we can just slightly try to tune in the different shape parameter, but we can model the region that we are interested in. So therefore, the log-normal distribution can represent the early value and also the steady state. Or the wear out. Regions in the whole lifetime for the one device. So we can consider by using the different shape parameter as a 1, as a 2, as a 3 here. So if you look at the literature, when people talk about the reliability, many people they use log-normal distribution. Of course, in the end, it becomes like the common sense that people know, yes, we can use a log-normal distribution, but it's a very limited people understand why we are able to use a log-normal distribution. It's not only as a mathematical tool, but fundamentally has a certain reason, and the reason is here. It's because of the Hazard function. The Hazard function can be tuned, the failure rate function can be tuned with consider the different sigma, the shape parameter, and that can allow us to have the very good flexibility to model the different phase of the lifetime of the product. And of course, the log-normal distribution function is not easily to do the hand calculating, so therefore the researcher has already employed as a graph. Let's call this one to try to give the flexibility that the people can easily try to look at this graph, and then to look at the result coming from the log-normal distribution. So here is one example here. We can consider this one with a certain median time to value, and then we can use this graph to indicate as the failure rate. This is the failure rate shown in the y-axis. So this will become the very interesting and then the useful plots. But more importantly, is that we need to further understand if we try to plot the log normal distribution and what would be the typical result that we can expect it. So this is a value time. This is a graph of the value time versus the value probability, which means the y-axis is CDF. This is a cumulative plot, so which means that you test, for example, the 1,000 of the testing device. And with a certain time, you can start to have seen the device will be value. So you try to plot all of the value versus the time. And then the y-axis is a cumulative value. So you have the 1% value, you have the 2% value until the 50% value. So the one that we have been mentioned when we talk about log normal, we are very interested in the one of the 50% value, where is here. This is a moment that the 50% of your device that have failed. And then this is a time as a 50%. This is time that the reach for your 50% fail here. So in this case, probably like when you operating your device reach for around 700 hours, then you can expect that there are around 500 devices fail. Right? So you test 1,000 devices in total, and you start to operate with a certain time, and with the times goes by, your failure rate will gradually increase, and then once reach to the 700 hours, you already have the 50% of your device, your product that fail, which will be the 500 device fail. And of course, what we are interested in is definitely not the 50% of your product fail, because in reality, what we are actually interested in is the condition less than 1%. So by using this graph, it's also interesting to extrapolate the 1% value. Where is this one? Right? This is the 0.01. That means this is a condition of a 1% fail. And then based on this graph, we can extrapolate the 1% value, the time to reach to the 1% value, which needed as 70 hours. If you buy the 1,000 device from the manufacturing company, and then for sure that if the manufacturing company tell you that our result indicate that 50% of the value, it takes 700 hours. For sure, this is not the information you are interested in. Actually, we are interested in that how many hours that can reach for the 1% value. So therefore, with this condition, this result shown me here suggests that if you try to operate this product for 70 hours for the operating or biasing, then you will start to reach for 1% value. And imagine the total testing device is 1,000, so 1% value will be the 10 device. Fail. And to be honest, the 1% value is not a good enough criteria is not strict enough, because for reality, if you fabricate 1,000 device, you operate for 70 hours, that already has a 10 device fail. But imagine that you produce a wafer, you produce device day and night, and million the device product you try to fabricate. So normally 1% can be considered as a relative larger criteria. And reality, in lots of cases, what we are looking for is a 0.01% value. But how do we estimate the 0.01% value? Therefore, by using this graph, giving us a way to extrapolate. So we can do the extrapolation here. And to extrapolate the condition to reach to the 0.01%. And then this is our targeting criteria that we hope that we want to understand that how long will induce for the 0.01% value, and then the result could be like say 10 hours. So that means T 0.01% is equal to 10 hours. So then the conclusion is that this whole product with a 1,000 device you fabricate, but you try to operate for the 10 hours operations, then you start to gather 0.01% values. And then that means that you fabricate 1,000 device, and as long as you use a device for the 10 hours, you will gather one device fail. Which is not very good, because of just only operating for 10 hours that already have the one device fail. And imagine this is a certain cell phone, certain electronics that you use every day, and then the 10 hours is very short compared to the normal operation time for all of the electronics. So ideally, if you consider this is a product that you will like to sell to your customer, so normally there's no customer would like to buy this product, because of the lifetime is way too low, that with only the 0.01% value, but the device can, the whole product can be only operate for the 10 hours. But this is a good illustration to let you know that why this distribution function is useful for us to analyze the lifetime with respect to the different value rate. So this is the case of the gallium arsenide laser that testing at the 70 Celsius degree. And in addition to the log normal distribution, there's another one which is also very important, that we call the Weibull distribution. And then the Weibull distribution is something that we are able to do the hand calculation, we are able to try to calculate and derive by ourselves. So the Weibull distribution is a 2-parameter distribution, and as shown in the equation as here. The PDF for the Weibull distribution is shown me here. So we have this beta t beta minus 1 exponential minus t over alpha beta over alpha and beta here, and where the beta and alpha are constant. And so in this PDF, we have the two important parameters, which is alpha and beta here. And normally we call the alpha as a time scale parameter, which is alpha. And also we also have the shape parameter, as shown here. And also once we have the PDF, then we can easily to get the result of the CDF, which is shown here. 1 minus exponential t over alpha beta. And this CDF function is very important. It's one of the most useful equations. We try to analyze the statistic distribution in the semiconductor in nowadays, even beyond the reliability. Of course, the Weibull distribution is very powerful to do the reliability modeling, especially for the lifetime. But right now we see that the Weibull distribution is getting very powerful to extend to another domain, as long as they have this random statistic distribution. The case what we are recently found out that the Weibull distribution is also very useful to modeling the ferroelectric dipole switching. If you are working in this field, I think some of you might be working in the ferroelectric memory. In the case with the ferroelectric memory, we have this dipole switching, but this dipole switching is also randomly has a certain distribution. And also recently we just found out that this Weibull distribution can be very successfully to model this dipole switching as well. So anyhow, once you know the fundamental of the Weibull distribution, is very useful for you, because later you will understand that it can be easily extended to the lots of cases in the semiconductor field. So as usual, we will first to talk about the PDF function, as shown here. And like we already said that the beta, which is a shape parameter, so therefore the PDF function will also highly depends on our beta. As shown here, this is larger beta, this is smaller beta. And then we can also plot the CDF function. And also, as the beta will highly influence the CDF function. And in the end, we can have this hazard function, where our beta is also highly influence this hazard function. So in the case of the beta is equal to 1, then actually this Weibull distribution will simplify and back to the case of the exponential distribution function, right? This is a beta equal to 1. And then if you still remember that in the previous consideration, the most powerful for the exponential distribution, because in the end the failure rate is constant. But also in the case with the Weibull distribution, this is beta equal to 1, that will become as a constant value. and this is beta equal to 1 is here. This is exponential distribution function. So therefore, we should consider the beta equal to 1, then we can, this Weibull distribution function will come back as an exponential distribution function. And with the case of the beta equal to 2, there's a very specific name that's called the Rayleigh distribution. So this is also the special case of a Weibull distribution function, and then the previous equation can be rewrite as here. But the most important part for the Weibull distribution is not the exactly how this function look like, but the importance of this Weibull distribution is in the same that how we understand from the previous discussion for log normal, like we were always interested in to use this specific distribution function to modeling the lifetime for the one product. And as we previously have been shown, the lifetime of the one product is generally can be considered by this best tube curve, where we have the 3 different phases here. So we have the infant mortality in the beginning, and we have a steady state in the middle. And then last one, we have the wear out here. So therefore, by considering the different beta, we are able to model the 3 phases as well. So for example, in the case of the infant mortality, which will be here, in the case of the beta smaller than 1. So we can have this equation, this distribution to model the infant mortality. And also, we should consider as a beta equal to 1, then we can model the second phase. And the last one with a larger beta larger than 1, then we can use this to model the wear out. So the idea is the same. The reason that the log normal and Weibull distribution are very popular and very powerful is because we have these 2 parameters. And these 2 parameters, especially the one, there's a one very important that we always call as a shape parameter. By tuning this shape parameter, we are able to model the different phases for the semiconductor from the beginning till the values. So here is a some of the example of the Weibull plot. This is a Weibull plot of the bonding pad corrosion. Increased failure rate, and then this is a case with a bonding pad. So now we can see when we talk about the failures, when we talk about reliability, we are not only modeling the pure device characteristic. The pure device characteristic might be due to the electrical result, might be due to the threshold voltage, it might be due to gate current, drain current. But at the meantime, we can also model in the certain related to the materials degradation. Like in the case here, the bonding pad corrosion is actually due to the materials degradation, and now in the end cause the resistance increase. So therefore, we can also use the Weibull distribution to do the modeling. But then you might start wondering that what actually the difference. How do we know that when we should consider the log normal and when we should consider the Weibull distribution? So that's a question we will start to explain, because log normal and the Weibull distribution sometimes can fit the most set of the data. So both log normal and Weibull distribution appear to fit the most set of the data equally, and this is the case with the light bulb wears out. This is the case when we consider the light bulb values here. So now we can see that it's indeed that in the case, if we look at the figure A here, this is the for sure the black dot is experimental result, and then this line is fitting, distribution fitting. So then we can see the left hand side is a log normal, and then the right hand side is a Weibull distribution. And then we can find out that it's indeed that most of the data set can be fitted by both of these distribution. For example, the log normal can have the best fitting in the case with longer lifetime, and then the Weibull distribution can fit it in the case of the shorter lifetime. Better fitted for the shorter time. And the log normal is a better fitted for the longer lifetime. Therefore, this poses a question that everyone should be careful that when we do the fitting, when we do the distribution fitting, of course, in the end, we can always get fitted with a certain part, but we have to understand what's the purpose of this fitting, because we have to understand the goal here. If we want to fit it for the, in this case, we want to estimate the light bulb value toward the long time projection here. We are interested in the case with a long time projection. Then for sure, in this case, the log normal characteristic, the log normal characterization is preferred in this case, because clearly we can see the log normal can be fitted with a better lifetime, with a longer lifetime. But on the other hand, if we are interested in the fitting with a lower value percentage, because in the end, as you know, this is a graph where I already explained. This is graph of the value probability versus the time. Especially, this is a graph for the cumulative value probability. So therefore, if we are interested in understanding of the low value percentage of all of your product. For example, if we are interested in as a 1% value, for example, this is a 1% here, and this is a 0.1% value. If we are interested, like you fabricate 1,000 devices, and then you would like to analyze what would be a lifetime to reach to the 1% or 0.1%, and for sure, the Weibull distribution here is better for this application. So the Weibull here is better for the low value rate fitting. So therefore, the first criteria to determine that whether we should use the normal or Weibull is we have to go back to understand that what would be our goal for this fitting. Either we want to have the better fitting for the longer time projection, or we want to fit it with the lower percentage values. So in addition to this fitting target and also all these mathematics, fundamentally, there's still some physics difference we need to consider when we talk about the log normal versus the Weibull. And here is very important because in the end, when we try to do the fitting, especially use this statistical distribution function, we have to also understand the fundamental physics might be fitted with this distribution or not, because in the end, the reliability is not only as the reliability fitting, reliability matters a lot with the reliability value physics here. So the log normal, of course, this is like a 1 decade of the understanding and then the experience that we have so far. So sometimes it's very difficult to trace back that when it's the first paper to come out with this idea. But after 1 decade, 2 decade study understanding, now we reach the consensus that the log normal distribution tend to apply in the case when we have this gradual degradation occurs over time. This is because this gradual degradation is coming from the diffusion effects. Corrosion process. And also the chemical reaction. So that's so far that the people understand that in most of the cases when we talk about the diffusion effect, corrosion process, and chemical reaction, it's likely the log normal distribution has a better fitting due to this gradual degradations here. So in the textbook, in the reference that I'm referred to, they actually mentioned that the case here, the early PNP transistor, bipolar, MOS transistor, and light emitting diodes and lasers are examples. But you have to understand the technology will change over time. The early value criteria, the early value mechanism might not be the same. The early fabrication of the device, we use a lot of diffusion process. We use a lot of the the metals that easily have the corrosion, and probably we are not really control the chemical. So this conclusion so far might not be true. So the interesting part for reliability is that we understand the fundamental, but with time goes by, with the generation goes from the for example the 90 nanometer process until 3 nanometer process, the mechanism will always change because our device structure is change, our bias condition is a change. So, but the reliability is always getting different, and that's why if you're working on reliability field, you won't afraid that you will not have the job, because as the time goes by, the reliability will become more and more challenging. And then because our architecture is getting complicated, our bias condition is getting more high, our equilibrium field is getting higher, and also the mechanism will change over time. But the one thing I'm pretty sure that nowadays still very people try to use the log normal to apply in the case where we will talk about later in this class. This is a value in the beginning we have been mentioned. This is value we call the mass transport induced value. So that's nowadays people still very often use the log normal distribution to understand, to model the mass transport induced value. And sometimes we also call this as electron migration issues. And we also have been already mentioned in the introduction that the briefly related to the electron migration or the mass transport induced value. And let's go back again to see why the log normal might be fitted for this value analysis. So imagine that we have this interconnection line here. And then, of course, the interconnection line will not be always go straight. We have a lot of the corner for this interconnection line. And once we start to apply the bias, the electrons will try to flow from the one direction to the another direction. For example, the electron will try to flow from left to the right. And if we consider this is a copper interconnection line, and we have already mentioned that the electron, once flow, the electron has lots of the momentum, and this momentum will try to transfer to the copper, and in the end, with a certain time goes by, we will see the copper will be moving with the same direction as electrons here. So then once the copper is moving, then but the total amount of the copper is the same. So if you have the copper will be moving from one region to the another region, that means the copper might be start to accumulate in a certain area here. So you will have, because you have the corner will always have a different flux. So once you meet some corner, that you will start to foresee that the atoms might start to accumulate layer, and this will form what we call the gear lock. And as I already said, the total amount of copper atoms are the same. So you have one side, you have the huge copper accumulated. That means that from the beginning, most of the copper has been moving away. Therefore, we can foresee this region will getting thinner and thinner. In the end, we might start to have these void formations. So that's the issue that we call the mass transport induced value. What does mass transport? Mass, it means that the copper is a mass. So you have a copper transport, then in the end induced value. And why we call it electron migration? Because it's all driven by electrons. And this phenomenon is very well fitted with the concept of the gradual degradation. And also, this is very fitted with the understanding of the diffusion effect. Later, when we talk about log normal, we'll talk about how the diffusion might play the role here. Because imagine that this is certain atoms moving from one side to the other side. So the degradation is gradually happen, and that's for sure there's a certain diffusion involved in. And therefore, that's why that this is a perfect example that we can consider to use the log normal distribution. So that's why that even nowadays, when we talk about this electron migration, this mass transport induced value, we still use the log normal very often. And on the other hand, the Weibull distribution appear to be the case where we have the concept that we call as a weak link. Weak link. And then the weak link actually means that this is first of the many flaws. So to understand the meaning of the weak link, we come back as a very simple cases. If you consider that you have lots of the rings connected with each other, and then this ring connected with each other will become as a chain. This is a series of a chain. 锁链. So, and what does mean the weak link? Because imagine that if there's a one suddenly broken in this region, and this is exactly what this text means, the first of many flaws. So suddenly you have the first broken here. So if you imagine this is a chain, so once you have a broken in the one place, that actually means that the whole chain is broken, right? So that's a case if you broken here, and that means that your whole chain is broken. And this is a concept that we call as a weak link. And why we call the weak link? Because you have a lot of rings connected with each other. That's just like the link. But the problem is always happen in the case where the first weak region, the first weak spots that are broken, and therefore the whole chain will be broken. So that's how we call this weak link. And this weak link concept is exactly fitted very well to the very famous reliability issues that we call the dielectric breakdown, capacitance failure, fracture in the ceramic. But in here, we are particularly focused on the dielectric breakdown. Why the dielectric breakdown is exactly similar to the case of this weak link, is similar to case of this series chain. So consider you have the typical MOSFET. We have the source and drain in a certain region. We have a source and drain here. And then on top of source drain, we have this dielectric. So that's our SiO2. And now you can try to divide the dielectric from the left to the right as small pieces as possible as you can. So the overall dielectric is considered as the connective of this small fragment with each other. Right, so we can make this as a very simple illustration that the whole dielectric is actually just a summation of all these small fragments that's connected with each other. But nowadays, if you try to apply the positive gate bias here, as we know, the positive gate bias that will start to invert the electrons in the channel. But suddenly, if there's a case, if you have the breakdown, you have the defect generation, you have breakdown in this small fragment like here. And therefore, all the electron, you know the current, the electron will try to flow in the region that has a low resistance, right? So anyhow, they will try to find a way to always try to flow in the region has a low resistance, and this region has a lot of defect, it's already breakdown, and that has a low resistance. And therefore, you will foresee all of the current of electron will try to flow in these small fragments. And that means if the first of these small fragments, small segment is the first of this small segment region that is broken, then the whole dielectric is broken. So that means this is also the same as we described. This is the first of many flaws. And once it is, although we divide by this dielectric is a lot of small segments here, but once a small segment is broken, and all of the electron will try to flow this small segment and then become a huge leak current, and then overall, no matter how good the other region, still, but the dielectric is considered as a breakdown. So this is the same case that we talk about, which is called the weak link. So that's why when we talk about dielectric breakdown, later we will talk about TDDB, time-dependent dielectric breakdown. We always use the wave distribution. This has been discovered and applied, I think, for the last 1 or 2 decades so far. Of course, there's some slightly modification of the wave distribution equation, which consider more and more side effect, but the general concept is still the same. We always use the wave distribution to model the dielectric breakdown, to look at the dielectric reliability issue. And we will talk about this, the real case, when we talk about the TDDB later. So this is also one of the very key knowledge that if you look at the literature, many literature, they just put as a wave distribution as a general consensus if they try to model the dielectric reliability. But no one talk about why we can use wave, because you might think that just probably a mathematical tool that people think is just way too common. But in the end, because the knowledge here is just too old, sometimes probably it's older than my age. But here is a reason. So it's still good to understand why we are able to use a wave in the certain reliability, why we're able to use a log normal in the certain reliability. And now we still have to figure out that how we are able to do the certain calculation, and especially if you be good that we are able to do some hand calculation by dealing with this complicated equation. And then one way we are trying to do it is that we always try to think about that how to make the nonlinear reliability function plot as a straight here. So that's always a certain mathematical tricks that if we can try to rearrange the certain factors, and then we can revise as an exponential function become linear function, that will be more easily for us to handle. So back to the case with wave distribution. So we got as this function, the ft is equal to 1 minus exponential t over alpha beta here. So the equation is actually not that complicated, just very difficult to plot him. But if we do some calculation, like show me here, we do the natural log. First we move this 1 to here and we put as a natural log. So then we got the natural log 1 minus ft is equal to minus t over alpha beta here. Then again we do another natural log. So we move in this minus to here and we do another natural log, and that will become natural log minus natural log 1 over ft, which in the end will be equal to beta natural log t minus beta natural log alpha here, which is here. Then we can consider this whole as a y is equal to mx plus b here. So therefore we can use this one. Then we got we consider this y is equal to nx plus b. Then the x is equal to natural log t, n is beta, b is minus beta natural log a. So therefore we can plot the equation, we can show this plot as y, which y will be this one, natural log minus natural log 1 minus ft. And versus the x-axis, which will be natural log t. So we can plot in this, or sometimes we use a log. It depends, but anyhow, there's no, it doesn't matter. So natural log or log versus the natural log t or log t. And because of this term, sometimes a little bit long, because for mathematics is called natural log minus natural log 1e minus ft. So sometimes we just give this a name. That's we call this as the wabbit. So by consider this y versus x, and therefore we can reform our data, and this data will be the straight line where we can get fitted so we can fit in this straight line, and then the slope will be equal to the beta, right? Because the slope is n is equal to beta, and then the interceptions here will be equal to minus beta natural log alpha, which is here. So next time, of course, for the people who look at this graph in the beginning, if we don't do this step by step, like the explanation, probably it would be very difficult to understand why the y-axis has to be shown like in this. But now I believe now you can understand why the y-axis, because you know the distribution function is already not as straightforward. It's always a complicated equation, but now even for the plotting, we reform as distribution function as a way like here. Sometimes it's very easily to be confused, but I hope now you will be able to understand, digest, and accept it, that why in the end it would look like in this way. Because by using this way, we try to make the nonlinear reliability function as a linear, and then we can fit it as a beta and also get the alpha as well. So similarly, I will not further do the explanation, because log normal is one that is not easy to plot in. But anyhow, we can also consider the here by plotting. We consider this way, then we can also get the linear and straight line to fit it with the log normal distribution function. One more thing we still need to further understand is that when we plot in the probability function, we might also face one issue is that we have lots of the value data. So if the value data are way too many abundance here, and there are many capital F to plot. So the capital F, which is CDF, there are too many CDF to plot, and that would be very difficult to generating the straight line here. So therefore, in the practical consideration, how do we make it as a Weibull plot? We have some very good estimation. So if there are only few values, so obtaining a good estimate of this statistic parameter will be not a problem anymore. And in here, we can consider this CDF can be obtained by ranking the exactly value time. And this is, however, a recommended way to estimate a statistically more accurate CDF or F value for the population. And this estimation, this approximation is how we call as a Bernard approximation. So this Bernard approximation is typically used to simplify the calculations of a median ranking here. So you always have to be aware of that when we talk about new concept, of course, in the beginning, we will use a very complicated equation. That's the starting point. But at a certain moment, finally, you always can come up with a simplified equation that allow us to have a more efficient estimation. And that's also the one of the case here that we can use Bernard approximation. So what is this approximation look like? So we have this CDF FTI. The I means that we have a different sample, that different device has a different failure time. Is equal to the first one is what we call the I minus 0.3, and then over the N plus 0.4. So what does I here? I is the order. So what is the order? 排序. So you have to first you test 100 device, and then you have to give the order of each one. So you have the first device, second device, third device. So that's the order. And what is the N? The N is a total testing number. And then the FTI here, the F here, just remind you that the F here is going to be later. Once we have FT, but the TI, that means the different order of the device. And then we will put this in this equation to make the Weibull plot. So now we get this, because as you know, the problem is that the T is also related to the different device. So then you got many F here. So then you can use this one to do the approximation, put in here. Then we can start to construct the Weibull plot. Later we will give the one example, then you can try to practice and you will understand what is actually the powerful of this approximation. So here is some of the experimental data, just let you have the certain idea. So then the left hand side is a Weibull plot, and the right hand side is a log normal. Both can be fitted in the good shape, but you have to understand what is your goal of your fitting and what is the fundamental physics behind the fitting, whether these fitting are actually fit the reason we choose a log normal or Weibull or not. But another very importantly is that we can actually consider to use this Weibull distribution or this statistic distribution plot, not only for the Weibull. This is a different kind of no matter what kind of distribution, but in anyhow, if we can try to analyze from the graph, and then we can use this way to understand the mechanism, that would be the perfect, because then we can combine the understanding of distribution with the physics mechanism here. So this is a graph of this still the same. Now we just try to turn in another angle, but still the y-axis is a value rate, and then the x-axis is values, and then the y-axis is time. So now we can see that there is a very apparently that there's two different distribution. So first one, we have distribution like this one. We have one distribution here. We have the second distribution here. And the experience always told us that if we see the different distribution in the one reliability of the value data, actually this distribution, the first distributions, this is happening in the case with less than 5 hours. And then the second distribution is happening between the 10 to 100 hours. So the first distribution in the case of the 5 hours actually already suggests that we might have the first mechanism. On the other hand, we see the second distribution happening with a longer time. And this actually suggests that we have the second mechanism. So therefore, when we do this statistics analysis, of course, in the beginning was coming from the mathematical purpose, for the modeling purpose, that we want to do the lifetime modeling, want to modeling the different phase of the semiconductor for the lifetime. But later we found out that actually this is statistics analysis more powerful than we expect, because this analysis also can remind us that if you see the distribution in the different time domain and you collect all the data, you see the different distribution, that always suggests that there's a happening for the different mechanism. We have to treat them. We have to understand in the different way. For example, it's very often to see that if you try to collect the one value data for the one particular semiconductor product with a short time, there's a one mechanism. This is happening in the case of below 5 hours. But with the longer time, we found that there is another mechanism that's happening between the 10 to 100 hours. So you cannot always expect that your product will only experience one mechanism, but the mechanism can be happen with respect to the different time. And therefore, from these two distribution data, that can give us a hint that we have the two values mechanism. So that's a point, that's a very important part that we try to extend our understanding beyond the pure mathematics distribution, because in the end we have to back to our goal is reliability value physics, because therefore we have to understand what will be the possible root cause this result. And then this is one example that we can use this distribution in the end to identify in this product we are suffering the two different mechanisms that can lead to the different distributions. Okay, so we will take a break and come back later.
那我这样子，我要测量它氧化之后的这个微两一样的纹理，那我要到底用多少换算的这个厚度去算？我要原本的呢，还是我要用？
你可能让 CV 先确认一下，你可能在量之前每颗都要先用 CV 确认一下它的等效电容，对，用等效电容去判断它到底有没有被氧化。
哦，这个有这个是吧？
对啊，用等效电容你就可以看到它的 case， 对，你就会估算它多少被氧化。
可是它这个一来是说估算 case 是可以，但是厚度好像有点困难，因为它
就要切体验。对，你只能借由切体验，再去搭配点式子，然后最后想办法估算出来。
calculation 这样。
对，因为这样的话，因为你这个氧化的每一颗都 calculation 也是有点距离的话，没有办法。对。
可是我这样就有很疑惑啊，就是说我这个是在 most cable 的情况下，我可以这样子去用这种估算，但是今天假设我做在元件上，我是一个 gate all around 的元件，因为 gate all around 其实我还可以不能填它，是因为它的这个 space。
我知道。
那我这样子，
你只能先用一般的 planar 的 CV 去做 calibrate， 把这个 database 建立。对，只能这样子，然后再去切这个 gate around 的这个厚度。
那我其实很好奇是为什么？假设我原本必须是给到7好了，然后我换算出来是大概是5，在5纳米的情况下做5MB的这个，那我为什么我弄完之后我不能用5去号称说我一样给一样的这个，用这个算出来的对差它可能变好之类的？
什么意思？
就是假设我这边我的力矩，
对，
号称它是给7，
对， 对，
它可以算出来大概5.5V的电场。那我为什么我不能说我被氧化之后，然后我一样是点7，然后一样去比较它变好？
可是因为你这时候的氧化产厚度不一样，所以等价就不一样。
那我今天有另外一个疑问，就是说，假设我今天不是 MOSFET 嘛，我是元件。
对。
那我元件上其实为什么会先定 High K 的厚度有一个原因，就是因为这个 gap 太小，所以我必须填得进去。
对。
那我今天我已经填进去了，我只是用后处理方式让它变成氧化层。那我这样子在元件的角度上，我都填进去了，那为什么我不能用 High K 的厚度去算？说我就是号称。
可是还不行啊，对啊。可是因为你的操作氧化程度不一样啊。对啊。可是你的等效 bias， 你 bias 给它，它这个元件它会分压在你元件上面就不太一样。
所以我不能号称是说，我不能号称是等电场。
对啊。
那我可以说我是以背上还可以厚度去做计算，因为我这个弄完之后，它一样是可以 work 啊。假设我的电晶体可以存，这样不行。
我觉得你说严谨方面可能会被 challenge， 严谨
会被指。可是如果说我们今天是这个电力做到手机或是什么这样，那其实我们工作给的反而是 VG 才是固定的，就是我的 house rate 才是固定的。
当然了，如果你做产品来说的话，它就不会 care 你，对吧？反正就是你这个你 follow 这个 roadmap， 然后你电压可以达多少，电力多少，
对啊，那没错。所以我就一直很好奇，说假设我有一天我需要去做一个这个撰写，那我要怎么去描述这件事情？我觉得
他一定会问你理由啊，他一定会问你理由，为什么你觉得你可以达到这个时候能达到这些电压，对吧？对吧？他一定会要你 show 一些 evidence。
或者除非我，譬如说我这个我用原本我做一次，然后用7的跟10的算出来的比例做一次，然后再去做一个交叉比较，也许会比较严重一点。
对。 Okay, so we'll continue. Next one we will like to introduce is related to the system reliability. So far we only deal with reliability and statistic analysis of the value for the individual device. For example, the individual transistor component or with a certain insulating. That's we only consider individual case. But in practice, we always use the multiple device. And the multi-component structure. So we use a multiple device or multiple component structure that are connected together and interact in the complex ways inside as one system. So therefore we have to consider the system reliability. So when we consider the system reliability, we have the two rules need to introduce. The two rules are needed to calculate reliability of the simplest type of the system. The first one is the multiplication rules. So this rule states that the probability that several independent events will all occur is a product of the individual event probability. Product of the individual event probability. So that's a multiplication rules here. And the second one is a complement rule. So this rule states that the probability that the event will not occur is 1 minus the probability of the event occurring. So actually, it's this complement rule is very easy for understanding. So if we have a 90%, the certain degradation will occur. And then therefore the 1 minus 19. This means that the event will not occur. So the idea here is very simple. So basically we try to apply these two very basic fundamental rules to understand the system reliability. So the first one is the system is by definition, it means that it consists of more than one component, and then we have to take into account the first one is a series system. So in the series system, we have the n individual, n independent components connected in series system. And fails if any of these the components fail. For example, we have this one, 4 components connected in the series system, and if fail, one failed, then the whole system fails. The whole system fails. So therefore, the system reliability can be expressed as the product of the individual reliability. So then this will be the product rule of series rule, and then the system failure function can be considered by reliability function is a 1 minus ft, and therefore the failure function is a 1 minus rt here, and therefore we can consider the rt in here, and that's how we calculate for system failure function. And then the failure rate, this is a failure rate, can be shown in here, and by consider this this one, then we can have this result as shown in here. So therefore, this equation suggests that the failure rate of a series system is the sum of the failure rate of an individual component. So it's a summation of the failure rate for individual component. And then the reliability of the series system is always worse than that of the weakest component, because if you have the, for example, like say you have a 97%, but now you have a 3 components that you have to 97% times 3 times, then you get always worse than the weakest component. So that's reliability of the series systems. And on the other hand, we have another one that we call the parallel systems here. So the parallel system means that we have the n independent components connected in parallel, and system fail when all components fail. So this is will be the parallel system. So the failure criteria is that we have to once all components are failed. For example, in the case with the following one, we have the 4 in parallel, and then this failure will be only happens if the system would like to fail, will only happen if R1 and R4 all fail. Then this system will fail. And also, parallel system sometimes we also call as a redundant system. So reliability of the parallel redundant system is always better than that of individual component. So it's always better. So for example, you have a 2 component with a constant failure rate around here. This is reliability after 1,000 hours for each single component. We got this of the 19.48%. But if we put it as a double redundant, so it means we put it as in parallel, then by consider this equation here. So therefore we got a 99.9. So we have the around 9% improvement. So I think the parallel case that's already very fitted with a daily life experience that you want to have some more backup in parallel, and then you can always increase the overall reliability. But the question is that the backup in parallel always cause additional cost issue, because you have to purchase 1 or 2 more that put it in parallel, and then you will have these cost issues. And next one, let's just talk more about this physical significance of the value distribution function. Because in the end, we still hope that we spend so much time to understand this distribution function, but in the end, we hope this the distribution function can provide some physical understanding. So that's a very important part. So back to the case where we talk about the weakest link. So if we consider a certain f, if the f is a probability of the length L, so that means if we consider a certain interconnection line or certain piece of the material, and then the overall length is L. So if the f is the probability of the length L, and then the 1 minus f is the probability of this is f is a probability of a length L breaking, then the 1 minus f is the probability of the survival of these lengths here. So now we can similarly have the survival probability of a small part for each individual. So therefore, we divide this length with a small fragments in individual, as shown here, and then each part is the arrow here. So therefore, the D arrow, because now we have the length, small length as a D arrow, so therefore each value for this D arrow is what we call the DF. So DF is a probability that length DL breaks here, and therefore the survival probability for this small DL is 1 minus DF. So therefore, the 1 minus F can be considered as a 1 minus df, and then L over dL. Because of now, if the dl in there is equal to L, then this, if this one equal to L, then this overall will become the same, like here. So we put it as a log, and then we can get this result here. And when df is approached to as smaller as possible, then the natural log 1 over df, 1 minus df lead to the df, and therefore the f here is equal to 1 minus exponential L times df over dl. So now the probability of the whole length breaking has a certain correlation between the probability of the smaller length breaking versus over this dl. So that's the purpose to first to come up with this equation. So the next one is we want to extend this equation to considering that there is a stressing, there is a bias factor here. So we can expect that the df over dl will physically depend on the applied stress sigma. The applied stress here can be, for example, electric field. That's the electric field. So we expect that this df over dl will physically depend on the electric field, the stress factor that we consider. So therefore, the dependency of F on L can be modeled in various ways, but it's common to assume a power law relationship, which is here. dF over dL is equal to this term, 1 over L0 times sigma over sigma 0 with m power here. So in here where L0 and then the n are constant, and therefore we can rewrite the previous equation the F is equal to 1 minus exponential minus L over L0 times sigma 0 m. So we can rewrite it as shown like in this way here. So now we will extend this equation to the case where we are interested in, particularly the dielectric breakdown. So in the case with a dielectric breakdown, the operating stress is electric field, and the electrode areas A. Because of the dielectric breakdown in here, we consider not only the length. This is a typical schematic for the MOSFET. And then on top of the substrate, we have this dielectric. But this is a two-dimensional graph. No, this is a one-dimensional. But if we try to plot as a, sorry, this is two-dimensional graph. But if we try to plot as a three-dimensional, then the reality is that the dielectric has a certain area. And now we want to correlate this one. We extend this L, which is the length, to the area, and therefore we can rewrite it. The equation F is equal to 1 minus exponential minus L. And now we don't talk about L anymore. We talk about A over A0, because now we consider the dielectric here. But the A0 is a small part which is here. So that's the A0 here, which is a small portion of the overall area. So therefore now the ideas here now transform to the value with respect to the area, and then we have this L0 here. So you have to start to transform the three-dimensional, but now you look at from the top view. So top view, then your dielectric become a plane with a loss of an area. So we have the total area of A. Then we have the small area of the A0 here. So therefore, by rewrite this equation, we consider as A with our bias as an electric field. Now we can have the result here, which is E over E0, and then the rest are the same. So now we finally have the chance to estimate the value F with respect to area. So now we can estimate the total F, the community value, with respect to the area factors here. And this consideration, why we can extend the previous, for this one, the weak link from the length here to the area here, because of in the case with the area, the weakest link consideration for the dielectric breakdown still will be true, because if we have the breakdown in here, then the overall current electron will try to goes only in this region. And then if the breakdown is happening in small a0, then the whole dielectric will be still the same breakdown. So that's we still consider this is a case of a weak link. So this concept is later when we talk about the time-dependent dielectric breakdown, you will start to see the many practical examples that are how people try to estimate the lifetime from the big area to the small area, or from the small area to the big area. And then the idea here is refer to this equation, because now we have the chance to convert the area to the value. So if we can understand the F of the A0, then we can easily convert to the A. And that's the purpose to consider this the value calculation with respect to the different area factors. So another one is when we talk about the understanding of the reliability, and then one thing we are very often use is to consider this Arenas model. And the Arenas model is very useful, and we can have the equation like here. The certain factor is correlate with constant exponential E minus RT, and it has not limited only to the NTTF, but it can be the any parameters that we are interested in. So lifetime for sure, but then the threshold voltage shift, and then the R, and also the unresisted or gate current. In anyhow, any parameter here, if we try to measure this, characterize this parameter with a different temperature, we can always get the Arenas model, and then in there we can calculate this activation energy. For example, in the right bottom figure, so we use this Arenas equation, then we try to extrapolate the activation energy of 1.03 electron volt. But how do we understand the physics, any mechanism that probably will contribute to this activation energy? So normally what we are doing is look at the literature, try to look at any mechanism has been reported with this related activation energy. So this 1.03 activation energy, which is very similar in this case, which is reported in the range between the 1 and 1.05. And therefore, this consistent value suggests that the mechanism here might be due to the service charge here. So that's one example that how in the past that we try to, in the end, to use calculated activation energy in the end to correlate with failure mechanism, because anyhow, no matter what kind of approach that we are doing, we use distribution equation, we use arenas model, we use no matter what kind of mathematics, in the end, the purpose is try to help us to understand the mechanism, failure mechanism. So this is how that the people, even nowadays, that we are very often to try to calculate the one activation energy, and then try to use the literature to infer that what kind of the mechanism could show the same activation energy, and therefore this mechanism could be the same responsible for these failures here. So this is the same one like a previous, so we don't have to talk about, but the next one will be interesting in is that again, if we see the activation energy that actually has a different slope with a different temperature, that also suggests that a different mechanism here. So the top figure is the value of a high electron mobility transistor with respect to the different temperature. So now we can see there's a different region has a different slope. With this temperature from 100 around 225 has a one slope. So in this temperature region, there's a one slope. On the other hand, when the temperature increases beyond the certain region, beyond the 225, we got another slope here. That's also, it's a very practical case in the very lots of semiconductor device. In the one temperature, you will trigger one failure mechanism, but when you heat up temperature beyond a certain criteria, then you will try to trigger another mechanism. Sometimes not only the high temperature, but also low temperature, you will also trigger different mechanisms. That's why when we do the product qualification, we have to do the very comprehensive, systematic temperature study, because of the different temperature in the end will cause a different reliability failure mechanism here. So in this graph, that suggests that in the temperature between the around 150 to 225, we got this kind of the temperature dependency of lifetime, and this suggests that if we try to convert the arena's plot, that would be in this region, and therefore we can estimate this one, which has an activation energy around 0.6 electron volt. And also, with this temperature around 225 and beyond 250, then we got another slope where we can have another activation energy can be calculated, as shown me here. That's a 2.2 electron volts here. So you have to be, when we do this reliability modeling analysis, has to be very careful about the slope. It's not necessary that we have to always fit it. Of course, if you try to consider, if you didn't if you are not aware of this slope change, you can still feed it with one activation energy for overall data. Although it's not fitting very well, but you can still get one. But you probably will get some misleading result because of this fitting. Actually, it's not truly reflects the mechanism. So we have to be divided by the two different fitting to get the two different activation energy, and then the two different activation energies suggest that we have the two different mechanisms. Especially the activation energy here, it shows a huge difference. If you look at the table showing the previous one, so you can see that we have this one sometimes has a 0.03, sometimes has a 1.4. So this very distinct activation energy always suggests that it has a different mechanism, and that's why in this graph we can also infer from this analysis suggests that we should consider in the one low temperature region what would be the failure mechanism, and another high temperature region what would be another failure mechanism dominating. Okay, so that's a main key takeaway from these slides. First, we talk about lots of statistical modeling. This is it's a experience like accumulate in the last 2 decades, how people try to leverage the statistical model to understand, to analyze results. For sure that it's always very difficult for every of you who first time to understand, but if you later have some more practical experience, you start to process your data, analyze your data, this can help you a lot. And then we talk about the several different distribution, and the most important one for us is log normal and Weibull distribution, and you have to be aware of that what's the fundamental reason that this is important, this is useful. Many people know that we have to apply log normal, we have to apply Weibull distribution, but nobody understand very clearly what's the fundamental reasons here. And then we talk about the failure rate, relative function, we talk about static process control, also some system, the concept related to system reliability, and also the physics model such as arenas and then weak links consideration that help us to try to infer from the mathematics, from the statistics to the understanding of the failure mechanisms. Okay, so then we will start to do some very small exercises. You just have to practice with me. That's important because, as I say, that the Weibull plot is one of the things you cannot avoid. If you are still stay in the semiconductor field, you cannot avoid the Weibull plot. You always will use as long as you are getting more and more in the close to the industry. So then we have to, but many people still very confused how to make the Weibull plot. Of course, there's already lots of available software that can help people to plotting, analyze, but fundamentally you still have to go through by yourself once. So this is example in the TDDB experiments. So we try to first to analyze the time-dependent breakdown. So then we consider the situation of we consider the case where we have the MOSFET here. And then we start to apply, we have the dielectric here. And then we apply the gate bias in the gate region. And we consider this gate bias, and then with the stress time is longer enough, we are very often to see this is a gate current versus the time. And with the stress time is longer enough, then we will see the time dependent dielectric breakdown as shown here. So when we try to process this time dependent dielectric breakdown, the first step is we have to extract it, the TBD data. So what's the TBD? The time to breakdown. So we try to extract the TBD data from each recorded IT. So the IT is the current versus time trace during the CVS. That's a constant voltage stress. And then, therefore, the TBD can be extrapolated when the current exhibits a state larger than a defined value. So for example, in the right hand side, if we consider the criteria is here, we consider the criteria as here, once the current is larger than this one, we consider as a breakdown. Then we can start to estimate the TBD. For example, here we have this one, the time to breakdown. So that's an example. On the other hand, we can also consider the criteria as a larger. If we consider these criteria, then we get the different TBD here. So when we do the analysis of the value data, it's also very crucial to know what is the definition of the value here. So here is an example that if we put a different current level, actually we will have a different TBD. But for sure that the how to define the good criteria, that's another big story. That's already people spend so much time to understand. We'll talk a little bit more about how to define the good criteria later. But in here, just let you know that there's data, what we call the TBD, the time to breakdown. Then what we have to do is to start to ordering the TBD values. Ordering the TBD value from the smallest to the largest one. So for example, we test here certain amount of data, and the first one is breakdown at 240 seconds, and second one is breakdown at 191, and then the third one is breakdown at 16. So therefore we do the sorting and ranking here. So once we do the ranking, which means we rank from the smallest to the large. So that's a ranking. So we have this randomly distributed data, but we're ranking from smallest to large. And then each one we put it as an index here. And once we have the index, then we can start to use this Bernard approximation. So where we have already mentioned before, the I here is the index. And then the N here is the total value numbers. Or the total testing device number, total testing numbers. Because sometimes we will only try to test until the fail. So the total number you test is equal to the total failing numbers here. So then in this case, we have the 10, this is an example with a 10 device fail. Device fail. So therefore the N is equal to 10. So therefore the calculation here is become very simple. The previous, if we don't take into account the Bernard approximation, the calculation of the FT is very complicated. But now with the consider the Bernard approximation, the calculation for FT is just become as a mathematics in the elementary school, which means the first one is 1 minus 0.3, right? So we have an index of 1. 1 minus 3, 1 minus 0.3 over the total, which will be the 10 device plus 0.4. So that would be equal to 0.067, which will be this one. That's our CDF here. So now you know that the powerful of this approximation, because in the end the calculation just way too simple. This is a calculation that the hand can be calculated, and the reason I show here because definitely in the homework, in the exam, you will be asking to make the wave plot. That's why that I do the explanation, more detailed explanation here, because this is something that you are able to manually calculate by yourself. Okay, so once we have the CDF for the each factors, each device value, so then we can just plot in here for the FTB. This is the data, so then we just put in this equation, and then we can get fitting as a beta and then eta. The eta here is just the same as the previous we say as the alpha. Some people use eta, some use alpha, but that's the same. In anyhow, that's the same meaning here. So finally, we are able to create this wave plot, and we are able to extrapolate the slope and then the interceptions. So therefore, it's your time. Try to calculate by yourself. This is a collection of the 60 laser diode. So that means N is 60 here, because in here we test the overall is 60, but then it's only 7 value occur here, and then this is a 7 of the TBD here, and then the Bernard approximation equation is shown me here. I minus 0.3, N plus 0.4. So therefore, what you have to do now is first do the I, and then do the ordering, do the ranking, do the FT. Okay, so if you have time, you can do it now. It's just give you 5 minutes. It's very simple, but it's very useful. because in anyhow you need to experience once. So the I is from the ordering. So we have the 1, 2, 3, 4, 5, 6, 7, and then what is the TBD for the 1? Okay, so first we do the small to largest ranking, so we will get the result. So the smallest one for TBD is 181 seconds, so we got the 181, 299. So that's a TBD from the smallest to large. That's the ranking here. And then we start to calculate FT. So then the first one is 1 minus 0.3 over, we got the 60 in total, plus the 0.4. So that will be equal to 0.012. So therefore, we can start to estimate FT for each one. And then we can start to put this F to plot the Weibull plot. Which is natural log minus natural log 1 minus Ft over the natural log T. So therefore you can check the textbook. This is an example in the textbook 4.3. And when with this linear line, you can fit with a beta and also the alpha. So the building the Weibull plot just simple, just show me here. It's not that complicated. Of course, the graph in the beginning, the plot in the beginning might look very complicated, and then the equation in the beginning might look very complicated, but in the end the calculation here is very simple. So we will stop here, and then from next week we will start to move on to the so far we mainly talk about the mathematics. We talk about lots of the statistic distribution, but starting from next week we will start to move into the new chapter. For this class we will be mainly focused on the physics mechanism and how do we do the testing and how do we understand the reliability. So we will start to talk about, and also the next week we will announce the schedule from the till the end of this semester, and then we will first to finish the presentation, and then for the final exam. So the presentation for the individual group will be request to do this before the final exam, and then next week I will also announce the information related to the group member. So I will just help you to make a group, and then next week you can start to talk with your group member to start to prepare for the presentation. Okay, so see you next week.